what we will see now is when the three charges are not placed in the straight line, in a straight line. So they may be placed as a general situation. They may be placed at the vertices of a right angle triangle or at the vertices of an equilateral triangle. We will do the first example with the vertices of a right angle triangle, and then another one with the vertices at equilateral. So let's suppose that we have a right angle triangle that the sides are, let's say that they are 12 centimeters, 15 centimeters, and then we have a charge QA that is positively charged with a magnitude of 3.20 times 10 to the power of negative 6 coulombs. And then we have the at vertices B, we have a charge QB that is negatively charged as 4.80 times 10 to the power of negative 6 coulombs. And at the vertex C of the right angle triangle, we have a charge C that is negatively charged with a magnitude of 5.30 times 10 to the power of negative 6 coulombs. And we will find what is, start with force net, electrostatic force net at vertices B, or charge B. So again, we will place ourselves to the charge of our interest, which in this case is charge B, and then we will take charges one by one. So to draw the free body diagram, and then we'll ask, if we are placing ourselves at charge B, what is the force that charge B is experiencing as a result of charge A, supposing that charge C doesn't exist? And this is the superposition principle. Since the two charges are opposite, then what that will be, attraction or repulsion? Will be attraction. Great. So along the line that connects the two charges, you will draw a force that is attracting. And I will say that this is electrostatic force A, just for simplicity. And then you will ask yourself, what is the attraction, or what is the force that B is experiencing as a result of charge C, supposing that charge A doesn't exist? Is attraction or repulsion? Is repulsion, because the charges are with the same nature, both are negative, so it will be a repulsion force. And this will be the force that charge C is exerting on charge B, supposing that A doesn't exist. Then we found the direction of the forces using the superposition principle based on the general law of electricity, which is the same charges will repel, opposite charges will attract. Now let's find the magnitude of those forces using Coulomb's law. So K, QA, QB over the distance between A and B to the power of 2. And for FC, we'll have K, QB, QC over the distance between B and C to the power of 2. Let's enter in the calculator the values for K, QA, QB, and distances, and calculate the value. Okay, notice here that we are using the sign of the charges to identify if the force that the two charges are experiencing is a repulsion or attraction. When we are calculating the magnitude, we are not using the sign of the charges. So you cannot say negative 9.59 newtons when you are calculating the magnitude of force A. And another thing is that we are calculating magnitude. Magnitude doesn't have a value. It's just a number. Magnitude is the numerical value. So I have for A as a 9.59 and for C as 11.12. Now, this is an easy situation, so you can kind of go by without making the table of components, because you have one force that is along the north axis and one that is along the west axis. So you can easily draw the resultant of those two forces as being this force here, which is the electrostatic force net at point B. Okay, but if you are not able to see it, and it's fine, you can still build the table of components and then find what is the horizontal direction, vertical direction, and then you will figure out that the horizontal direction is negative 11.12 and vertical direction is positive 9.59. So when you are finding the magnitude of force net, electrostatic force net at point B, then you will go the square root of 9.59 to the power of 2 plus 11.12 to the power of 2. And this will 14.68 newtons. And then you can find either angle alpha or angle beta, whatever angle you want. You will see that angle, let's say angle alpha is the inverse tangent of opposite, which is 9.59 over 11.12, and will be inverse tangent 9.59 over 11.12 equals to 40.8 or 7 degrees. And then you can state that force net, electrostatic force net at point B, or charge that is on the vertices B, is 14.68 newtons at 40.8 degrees, and this will be north of west. Now we will calculate what is the electrostatic force net at charge A. Okay, so this is more complicated. We cannot kind of omit or avoid creating the table of components. So one way or the other, we have to figure out what is the table of component and the horizontal component and vertical component of the forces at point A. But let's start with the free body diagram at vertices A. So again, we will use the superposition principle. So we'll say, what is the electrostatic force that A is experiencing as a result of B, supposing that C doesn't exist. Since they are opposite, then will be attraction. So this will be the force that A is experiencing as a result of B. And then what is the electrostatic force that A is experiencing as a result of C, supposing that B doesn't exist. Since those two are opposite charges, then we will have attraction force as well. And again, when we draw the force, we draw an imaginary line between the two charges, and this will be on that line, we will have the force that the charge is experiencing. If it is attraction, then will be toward the charge, the other charge, and if it is a repulsion, will be away from the charge. Let's calculate the magnitude of each of them using Coulomb's law. So K, Q, A, Q, B over distance between A and B to the power of 2. And this will be K, Q, A, Q, C over the distance between A and C to the power of 2. So from this formula, we know what magnitude of A and B charges are, but we do not quite know what is the length of between A and C. However, using geometry, we can find that the length between A and C to the power of 2 is whatever is AB to the power of 2 plus whatever is BC to the power of 2. Notice here that we are looking for this distance AC to the power of 2 in this in our formula. So we don't even need to square root the result that we have here, but we can simply say 12.0 to the power of 2 plus 15.0 to the power of 2, and this number will be the distance between A and C to the power of 2. So 12 to the power of 2 plus 15 to the power of 2 will be 369 centimeters squared. Okay. So the distance between A and C to the power of 2 is 369 centimeters squared. And when we are converting this into meters squared, because it needs to be in meters, then we are multiplying this by 10 to the power of -4. We need to convert the distance in meters, not just centimeters. You can choose to go 0.12 to the power of 2 plus 0.15 to the power of 2, and that will be the same, should be the same result. Now in your calculator, enter those values and find what is the force that B is experiencing and what is is exerting on A, and what is the force that C is exerting on. The last piece that we have to figure out here in terms of the geometry is we have to figure out what is this angle here. So let's call this angle alpha or theta, you call it whatever you want. And in order to do so, what we will or we must do is that we must find what is this angle alpha here. So now this angle alpha, since we have a right angle triangle, we can find it as the inverse tangent of 15.0 centimeters over 12.0 centimeters. So this will give us the angle that is between the south axis and the force C that we have here. So based on the calculation is 51.34 degrees. And now if we are going to state like as a vector those two forces, then we will have force that B is exerting on A will be 9.59 newtons going south, straight south, and force that C is exerting on A will be 6.20 newtons at 51.34 degrees, and this will be east of south. So now in order to figure out what is the force net at charge A. Force net, like in every case, is the vectorial sum of all the forces that the object is experiencing. So will be FB plus FC. Since this is a 2D situation, then what we do is we build the table of components. So after you build the table of components, you should have for the horizontal as for the horizontal of FB will be 0 and vertical will be negative 9.59. And for the horizontal of C will be sine, because horizontal, you have a force FC that goes like this, FC with this angle here. So the horizontal will be positive of sine of that angle, and the vertical will be this one here, will be negative as cosine of the 6.20. Then you will find the horizontal and vertical as 4.84 and negative 13.46. And the magnitude of the force will be the square root of 4.84 squared plus 13.46 squared, so 14.30 at 70.2 degrees south of east. As a homework for you, I will ask you to find the force net at point C, or vertices C. The other case that is very common when we are dealing with the applications of Coulomb's law is when we are finding the electrostatic force net of a charge when the charges are placed in the vertices of an equilateral triangle. So an equilateral triangle is a triangle that three sides are equal to each other and the angles are equal to each other and they are all 60 degrees. So what do you see in an equilateral triangle, even though that this doesn't look quite equilateral, is that the lengths are equal to each other and the angles are all 60 degrees. They are all equals to 60 degrees. What we are doing here is we are placing charges on those vertices of the right equilateral triangle. So let's suppose that we have a situation like this when we have an equilateral triangle and the vertices are A, B, and C. And the distance, the side of the length of the sides of the equilateral triangle is, we are placing charges that are like this. QA is equal to negative 2.85 times 10 to the power of negative 6 coulombs. QB is positive 3.72 times 10 to the power of negative 6 coulombs. And QC is positive 4.83 times 10 to the power of negative 6 coulombs, while the length of the sides of the equilateral triangle, so AC is equal to AB is equal to BC equals to, let's say, 15 centimeters. And what we are doing initially, we are finding what is the electrostatic force net at charge A. So we have a charge A that is negative, charge B that is positive, charge C that is positive. We will draw the free body diagram that charge A is experiencing using the superposition principle. So what is the force that A is experiencing as a result of B, supposing that charge C doesn't exist? Since the nature of the two charges is opposite, then the force will be attraction force and will be along the line that connects the two charges A and B. So this line here, AB, and this force here, FB, will be parallel to each other. And then you say, what is the electrostatic force that A is experiencing as a result of C, charge C, supposing that B doesn't exist? And again, since the two charges A and C are opposite charges, then the force is attraction, and it is a force that looks like this along the line that connects the points A and B, the vertices A and B, where the charges are placed. So AC is parallel to the electrostatic force that A is experiencing as a result of C. So what do we have here in terms of the angles is that this angle here is 60 degrees as well, and this angle here is 60 degrees. So if we are writing those two forces as a statement, as a vector, then we will have the electrostatic force that A is experiencing as a result of B will be whatever is the magnitude at 60 degrees, and this will be south of west. And for the electrostatic force that C is experiencing as A is experiencing as a result of C will be whatever is the magnitude that we will calculate using Coulomb's law at 60 degrees, and this will be south of east. So now let's calculate the magnitude of the forces B and C using Coulomb's law. So K, QA, QB over the distance between A and B to the power of 2, and K, QA, QC over the distance between A and C to the power of 2. So then the magnitude of FB is 4.24 newtons, and the magnitude of FC is 5.50 newtons. So this is obviously a 2D situation. So the best way to figure out what is the force net is to build the table of components. When we build the table of components, we keep in mind that FB is between south and west, which means that we will have negative and negative, both horizontal and vertical. And then for FC being between east and south, then we will have the horizontal positive and the vertical is negative. And then using sine and cosine, cosines for the horizontal and sine for the vertical, we will find the values of FB and FC on the horizontal and vertical. After we find those two, we compose the vector with those components. And this vector will be somewhere between south and east because the horizontal is positive and the vertical is negative, and the magnitude will be 8.45, while the angle will be the inverse tangent of 8.43 over 0.63, which is 85.7. And when we state that value, then will be the force net at point A will be 8.45 newtons at 85.7 degrees south of east.